At a silent point in space nearly 1.5 million kilometers away from Earth, where the gravity of the Sun and Earth balance perfectly, a telescope opened its eyes and delivered data so unsettling that scientists immediately realized modern cosmology could be standing on unstable ground. This was not another pretty photograph of distant stars. The Euclid Space Telescope may have just revealed that the universe does not behave the way physics says it should. The European Space Agency's Euclid Observatory transmitted its first complete scientific observations back to Earth. The data arrived at research centers like the Space Telescope Science Institute in Baltimore, where scientists checked every instrument again and again. Not because the hardware failed, but because the results were almost too perfect. The measurements exceeded expectations so dramatically that researchers immediately understood they were looking at an extraordinary crisis. For centuries, humanity believed the universe was mostly made of stars, planets, galaxies, and glowing clouds of gas. Everything seen through traditional telescopes appears bright and physical, but modern physics tells a very different story. All visible matter, every galaxy, every star, every planet, and every atom inside your body makes up only about 5% of the cosmos. The remaining 95% is completely invisible. It cannot be seen directly, it does not glow, and it does not reflect light. Yet, somehow it controls the structure and evolution of the entire cosmos. Scientists call these hidden components dark matter and dark energy. Dark matter acts like invisible gravity, holding galaxies together and shaping the large-scale structure of space itself. Dark energy appears even stranger, pushing the universe outward and accelerating cosmic expansion faster over time. Together, these unseen forces determine the ultimate fate of existence itself. Whether the universe expands forever, collapses inward, or slowly fades into total darkness depends almost entirely on things we still do not fully understand. This is precisely why the Euclid mission exists. Unlike traditional telescopes built mainly to capture visible objects, Euclid was designed to map what cannot be seen directly by studying how invisible matter bends and distorts light across enormous cosmic distances. This effect, known as gravitational lensing, allows scientists to trace the hidden skeleton of the universe. Euclid does not simply photograph galaxies. It measures how their shapes are stretched by gravity from unseen matter spread across billions of light years. The first images were unlike anything scientists expected. In a single field of view, Euclid captured more than 100,000 galaxies. Then, using infrared observations beyond human vision, it identified hundreds of thousands more hidden objects. These were detailed measurements of the invisible architecture holding the cosmos together, and that is where the problem began. The patterns inside the data did not fully match existing models of cosmology. The clustering of galaxies appeared denser in certain regions than predicted. Gravitational lensing effects looked stronger than expected, and the distribution of dark energy showed unusual deviations from standard theories. Individually, small discrepancies might not sound important, but across measurements this precise, repeated consistently over enormous distances, even small differences become deeply unsettling. If these measurements are correct, one of two possibilities must be true. Either scientists fundamentally misunderstand the nature of dark matter and dark energy, or the laws of gravity themselves behave differently across the largest scales of the universe. That second possibility terrifies physicists because for more than a century, Albert Einstein's theory of general relativity has explained gravity with astonishing accuracy. It predicts how planets move, how stars bend light, and even how black holes behave. But Euclid's observations are beginning to hint that gravity across cosmic distances may not follow those same rules perfectly. If that is true, the foundation of modern cosmology requires a major revision, and the consequences reach far beyond astronomy into our core understanding of reality. If gravity changes at cosmic scales, then our understanding of space-time itself is fundamentally incomplete. Theoretical frameworks involving modified gravity, hidden dimensions, topological defects in space-time, or entirely new forms of physics suddenly move from speculation toward serious possibility. Ideas once considered exotic may become necessary explanations, which is why scientists around the world are watching Euclid so closely. Every galaxy it measures becomes another piece of a massive puzzle. Every distorted beam of light reveals how invisible matter is distributed across the cosmos, and every redshift measurement tells researchers how the universe expanded across billions of years of history. By the end of its mission, Euclid will map billions of galaxies across nearly 1/3 of the observable sky. The scale of this project is almost impossible to imagine, and with every new observation, one terrifying question grows louder inside research institutions worldwide. What happens if the universe is not built the way we thought it was? If the data continues pointing in this direction, humanity may soon face the biggest scientific crisis since Einstein overturned Newtonian physics. And what Euclid discovers next could determine whether our current understanding of physics survives at all. For 400 years, humanity has explored the universe while seeing only a tiny fraction of what actually exists. From the moment Galileo Galilei pointed a primitive telescope toward the night sky, we believed light would eventually reveal every secret of the cosmos. We built larger mirrors, stronger observatories, and more advanced instruments, convinced that if we looked far enough and clearly enough, the universe would finally make sense. But Euclid is now forcing scientists to confront a disturbing reality. We may have been observing existence with one eye closed the entire time. The stars scattered across the night sky feel immense to us, and entire galaxies appear unimaginably large, yet all the glowing matter we can directly observe represents only a thin surface layer floating on something far deeper and stranger. Beneath it lies an invisible framework stretching across the universe like a hidden skeleton. Dark matter forms gigantic filaments connecting galaxies over billions of light years, while dark energy quietly drives space itself apart faster every second. Together, they dominate the cosmos completely. Euclid was built to expose this hidden structure from its position at the Lagrange point 2 region, nearly 1.5 million kilometers from Earth, where the telescope operates in extraordinary silence and stability. Far from Earth's heat and interference, Euclid measures tiny distortions in light with incredible precision. Its mission sounds almost impossible when simplified into ordinary language. Euclid studies invisible matter by observing what invisible matter does to visible light. That process begins with something called gravitational lensing. Imagine a photon leaving a distant galaxy 10 billion years ago, long before Earth even existed in its current form. That tiny particle of light traveled across expanding space for billions of years, passing through enormous regions filled with dark matter. Even though dark matter cannot be seen directly, its gravity bends space itself, altering the photon's path. By the time that light finally reaches Euclid's instruments, the galaxy appears subtly stretched or distorted. The change is unbelievably small, measured in angles so tiny they are almost impossible to imagine, yet Euclid can detect them across billions of galaxies simultaneously. This is where the telescope becomes revolutionary. When researchers combine all these measurements together, they construct a three-dimensional map of the invisible universe itself. Suddenly, dark matter is no longer just a theory written in clean equations. It becomes a visible structure through its gravitational effects. Scientists can now trace giant cosmic filaments connecting galaxies across enormous distances, identifying massive concentrations of hidden matter and vast empty voids where almost nothing exists. For the first time in history, humanity is seeing the hidden scaffolding holding the cosmos together. But the deeper Euclid looks, the stranger the results become. The structure it reveals does not perfectly match predictions generated by modern cosmological models. Advanced computer simulations developed at institutions like the Massachusetts Institute of Technology, Princeton University, and Stanford University attempt to recreate the evolution of the universe using known laws of physics. Scientists input dark matter, gravity, cosmic expansion, and billions of years of virtual time into these supercomputers, generating predictions for how galaxies and cosmic structures should appear today. Until now, those models matched observations reasonably well, but Euclid is changing that balance. The clustering of matter in some regions appears too intense, while other areas look more empty than expected. The cosmic web itself seems different from what theoretical physics predicted. The discrepancies are not enormous at first glance, perhaps 5 to 10% in some measurements, but in cosmology that margin is deeply significant because our understanding depends on extreme precision. A 5% deviation across cosmic scales suggests something fundamental is missing from our theories. Either dark matter behaves differently than scientists assumed, or gravity itself changes behavior across enormous distances. Both possibilities would force a complete rewrite of modern physics. Suddenly, theories once considered fringe ideas are being discussed much more seriously. Some physicists believe gravity may weaken or strengthen differently across cosmic distances than Einstein predicted, while others propose entirely new particles or forms of matter beyond the standard model of particle physics. More radical theories suggest hidden dimensions folded into space-time itself, invisible layers of reality influencing gravitational behavior in ways humanity has never directly observed. This is no longer just theoretical speculation hidden inside academic journals. Euclid is producing observational evidence precise enough to challenge existing assumptions directly. The telescope is only getting started. Every new galaxy observed adds another crucial measurement. Every distorted beam of light strengthens the emerging map, and every gravitational lens becomes another clue pointing toward whatever invisible forces truly shape the cosmos. Researchers are processing enormous streams of incoming data continuously, searching for patterns that either confirm modern cosmology or expose deep cracks inside it. What makes this moment so important is not simply that Euclid may discover something new, because science discovers new stars, exoplanets, black holes, and galaxies every year. Euclid threatens something much larger. It may reveal that the equations humanity trusted to describe reality itself are incomplete. If that happens, the consequences will spread across every single branch of physics. Changing gravity means changing our understanding of black holes, cosmic expansion, space-time, quantum mechanics, and perhaps even the origin of the universe itself. The implications reach from the largest structures in existence all the way down to the smallest subatomic particles ever studied. For the scientists analyzing Euclid's data late into the night, this is no longer just another astronomy mission. It is becoming a direct investigation into whether modern physics can survive its most precise test ever attempted. The deeper Euclid looks into the universe, the more dangerous the questions become. What began as a mission to map dark matter is turning into a direct challenge to the foundations of modern physics, because the telescope is uncovering signs that the universe itself may have evolved differently than scientists believed possible. Right now, inside research laboratories across the world, teams of cosmologists are comparing Euclid's observations against the most advanced simulations ever created, feeding them every major ingredient of the modern cosmological model to see if virtual universes recreate reality. The goal is simple. If the laws of physics are correct, the simulations should recreate the large-scale structure of the real universe. But Euclid's data shows something unsettling. The cosmic web appears more uneven than expected, with certain regions containing stronger concentrations of matter than models predicted, while other areas contain enormous voids larger and emptier than simulations allow. Even more concerning, the patterns of gravitational distortion measured across distant galaxies suggest that dark matter may not be behaving like the invisible, slow-moving substance physicists expected. That possibility changes everything. For decades, scientists assumed dark matter was made of hypothetical particles, often called cold dark matter, which were believed to move slowly, interact weakly, and shape galaxies primarily through gravity. Entire cosmological models were built around this assumption, and massive underground detectors were constructed to search for these invisible particles directly. Billions of dollars and decades of research focused on finding them, yet Euclid's observations raise a deeply uncomfortable question. What if dark matter is not what we thought it was at all? If dark matter behaves differently than expected, then the entire history of cosmic evolution needs revision. Galaxies may have formed through different mechanisms. Large-scale structures may have evolved under unknown physical influences, and even the expansion history of the universe could require re-examination. Then there is the even more terrifying possibility. What if dark matter does not exist in the form scientists imagine because gravity itself behaves differently across cosmic distances? This idea has existed for years at the edges of theoretical physics through modified gravity theories arguing that Einstein's equations fail on cosmic scales. Under these theories, the strange motions of galaxies and cosmic structures are not caused entirely by hidden matter, but by gravity-changing behavior under extreme conditions. For decades, these ideas remained controversial because observational evidence was limited, and most measurements could still be explained reasonably well using traditional dark matter models. Euclid is now changing that balance by measuring cosmic shear with extraordinary precision. As light from billions of distant galaxies travels through space, invisible gravitational fields slightly stretch and distort those galaxies' shapes, allowing Euclid to reconstruct matter in 3 dimensions. Think about how incredible this technology really is. Humanity has built a machine capable of revealing invisible structures spread across billions of light years by measuring microscopic changes in ancient light. According to early observations, the resulting map does not perfectly align with current theories. At places like the Jet Propulsion Laboratory, scientists are combining Euclid's findings with data from the James Webb Space Telescope. While Webb specializes in studying individual galaxies and early cosmic history in remarkable detail, Euclid maps enormous regions of the universe simultaneously. Together, these instruments are creating the most complete picture of cosmic evolution humanity has ever attempted, and that picture contains serious cracks. If gravity changes at large scales, the implications spread through nearly every area of theoretical physics. Black hole behavior may need revision, quantum gravity theories could require new mathematics, and string theory models involving extra dimensions may suddenly become more relevant. Concepts once considered speculative could become necessary explanations for real observational data as physicists reconsider hidden dimensions or space-time defects left behind from the Big Bang. These are no longer philosophical discussions. Euclid is turning them into measurable scientific possibilities. This is why the telescope matters so profoundly. Most space missions expand knowledge gradually by refining measurements, improving accuracy, and filling gaps in existing understanding. Euclid is doing something far more disruptive by exposing weaknesses inside the framework modern cosmology depends on. The universe is becoming harder to explain using the theories humanity trusted for generations. Every day, more data streams back from deep space, and every week, new analyses appear as researchers test the measurements for errors. They are searching desperately for instrumental errors, computational mistakes, or statistical anomalies that might explain the discrepancies because the alternative is difficult to accept. If the observations remain consistent, modern physics may be approaching another historical turning point, similar to the moment when Newtonian mechanics failed to explain the orbit of Mercury and Einstein introduced relativity. Except this time, the crisis may be even larger, because for years dark energy was treated like a fixed, mathematically stable background feature of the universe that acted as a constant force pushing space outward. Dark energy was strange enough when viewed as a constant force accelerating cosmic expansion, but Euclid is now forcing researchers to ask an even more unsettling question. What if dark energy itself changes over time? That single possibility would shake cosmology to its core because dark energy determines the ultimate fate of the entire universe. It controls whether galaxies drift apart forever, whether cosmic expansion tears matter itself apart in a big rip, or whether expansion eventually slows down and reverses into a big crunch. When astronomers first discovered that the universe's expansion was accelerating instead of slowing down, the results stunned the scientific world. Gravity was expected to gradually pull galaxies closer together over time, but distant galaxies were actually moving away faster and faster. Something unknown was overpowering gravity on cosmic scales, and that unknown force became known as dark energy. Since then, the standard cosmological model assumed dark energy behaves consistently throughout space and time, but Euclid was specifically designed to test that assumption with unprecedented precision. By measuring the positions, shapes, and redshifts of billions of galaxies across cosmic history, the telescope can reconstruct how expansion changed over billions of years. Early signs suggest the expansion history does not perfectly fit existing predictions. Some measurements hint that dark energy could vary slightly across different regions of the universe, while other observations suggest the acceleration rate may have evolved differently over time than expected. Individually, these anomalies remain subtle, but together they form a growing pattern researchers cannot easily ignore. This is where cosmology becomes deeply uncomfortable. If dark energy changes over time, the mathematical simplicity supporting the modern model of the universe breaks apart, making elegant equations physicists relied on for decades incomplete. Entire theories about cosmic evolution would require revision, made worse the fact that scientists still do not actually know what dark energy is physically. We infer its existence only through its effects on cosmic expansion, meaning humanity discovered that most of the universe is controlled by something we cannot identify. Now, Euclid is suggesting that this unknown force behaves even more strangely than previously imagined. At observatories worldwide, teams are analyzing massive streams of incoming data where every observation contributes another piece to a giant cosmic timeline. Researchers compare how galaxies clustered in the ancient universe versus how structures appear today, tracking how gravitational lensing changes across different epochs of cosmic history. The deeper they look, the more difficult the universe becomes to explain cleanly, prompting some physicists to revisit radical theories involving dynamic dark energy, new quantum fields, or interactions between dark matter and dark energy. Others move into even stranger territory involving hidden dimensions beyond observable space, proposing that gravity may leak between dimensions, or that our universe exists inside a higher dimensional structure affecting expansion. These ideas sound extreme, but Euclid forces scientists to take them seriously because observations always matter more than assumptions. Nature does not care whether human theories feel elegant or comfortable. If the data disagrees with the model must change. To stay updated on these world-changing discoveries as Euclid continues mapping the dark universe, make sure to like this video, subscribe to the channel, and hit the notification bell so you never miss an episode.